Hello, today we're going to talk about periodic trends. First, we need to talk about Coulomb's law. Coulomb comes up all of the time in AP chemistry, and his law depends on two things: the size of the charge and then the distance. So let's talk about that. Size of the charge will refer to if it's like a +1 charge versus a +2 charge versus a +3 charge, or even if it's negative, or like a 1 minus, 2 minus, or 3 minus. The greater the charge, the greater the attraction between the substances, whatever they are, or between the particles, really. So yeah, the greater the charge, the greater the attractions. And then distance is kind of the opposite effect. If two charged particles are really close to each other, that's going to have a large attraction. Whereas if they're further apart, it's going to have a smaller attraction. So as the size of the charge increases, the attractions increase. As the distance decreases, the attractions increase. And again, so that means if you have smaller particles, smaller things can get physically closer together than larger things can. So that affects the distance as well. We also need to talk about something called effective nuclear charge. So nuclear charge talks about the charge of the nucleus, which of course refers to protons. Protons in the nucleus are positive, neutrons are neutral, so the neutrons don't affect it. But protons in the nucleus are affecting the nuclear charge. However, when you're talking about atoms of significantly different sizes, I'm going to use Bohr models to illustrate this because it's easier to visualize. Just remember that Bohr models are not perfectly accurate. Oops. There we go. All right, so let's say we have lithium, which has 3 electrons, and sodium, which has 11. So there are your Bohr models for lithium and sodium. They both have 1 electron in the outermost shell. We call those valence electrons. But lithium has 2 electrons in between. I'll use a different color to illustrate those 2 electrons in between the nucleus and that outermost electron. Sodium has just 1 electron in its outermost shell, but instead now it has 8 electrons in between. So even though lithium has just 3 protons and sodium has 11 protons, sodium has a much larger nuclear charge, they wind up having fairly similar effective nuclear charges because sodium's extra electrons that are in between kind of block the outermost electron from feeling as much of the proton charge. So it's kind of a weird concept, but we're going to talk about effective nuclear charge most of the time. So yeah, and it's all based on Coulomb's law. So even though sodium has a much greater actual charge, the distance there and the interference from the other core electrons will both affect the actual attraction felt by that outermost electron from the nucleus. Let's review really quickly what ionization energy means. It's the energy required, I'm going to use a big E for energy required to remove an electron from an atom. We usually start with first ionization energy, which just means how much energy does it take, ionization, there we go, ionization energy. The energy required to remove the first electron from an atom, or the outermost electron from an atom. So if we go back to lithium, and again I'm using Bohr models, but if I were looking at lithium, the first ionization energy would be the energy required to remove this electron. And then, the second ionization energy, you'd have to be the energy required for this second electron. Most of the time we're going to be talking about first ionization energy, but not all of the time. And it's affected by 2 things. It's whether you're talking about elements in the same group on the periodic table. Let me redraw that. So there's a periodic table. Elements in the same group versus elements in the same period. Now, if you're dealing with elements in the same group, What's going to matter is the number of energy levels. Let me draw sodium really quick. Sodium, again, has an extra energy level compared with lithium. Okay. They still have pretty similar effective nuclear charges because of Coulomb's law, the distance there, and the blocking or the shielding from those core electrons. So what makes a difference then is the distance. So the distance between the valence electron, or the first electron to be removed, and the distance for the first electron in sodium, the distance is going to be greater in sodium distance. So because there's a greater distance, it will have a weaker attraction, which means it will have a lower ionization energy. Lithium, on the other hand, you have a smaller distance, so you'll have a stronger attraction, and therefore a larger ionization energy. And again, that's for elements that are in the same group. You're going to be looking at the distance based on the number of energy levels. Now let's talk about elements that are in the same period. So let's redraw some of this. Instead of sodium, let's look at beryllium, because lithium and beryllium are in the same period. Lithium has 3 electrons, 3 protons. Beryllium has 4 electrons and 4 protons. So 3 electrons, 3 protons, 4 electrons, 4 protons. But they have the same number of energy levels. So you have a very, very similar distance between the valence electrons and the nucleus, very similar distance. So we can't use distance as our justification. We'd have to use the size of the charge. So the size of the charge here, you have 3 protons attracting that valence electron versus 4 protons. Because it has a larger charge, it will have stronger attractions and therefore a larger ionization energy. Lithium has a weaker charge, so weaker attractions, and therefore a lower first ionization energy. So once in a while they'll ask about successive ionization energies. That's when you're talking about first ionization energy versus the second ionization energy versus the third ionization energy, and etc. So those are removing from the same atom the first electron, second electron, third electron, etc. I'm going to use lithium as an example again. So lithium's first ionization energy will be removing that valence electron. The second one to be removed must be one of those core electrons, and the third one to be removed is that very last electron. So lithium only has 3 ionization energies. So the first ionization energy is always the lowest for any atom. First ionization energy is always the lowest. It's the easiest to remove the first electron. From there it gets harder and harder, so it takes more and more energy to remove electrons. And that's really based on the number of protons or the charge, the size of the charge. If I have 3 electrons, 3 protons, each of those protons is pulling on it fairly evenly. But once I take one of the electrons away, now I have 2 electrons, but still 3 protons. So each of the protons is pulling on those 2 electrons just a little bit more attraction. And then if I just have 1 electron, I see even more of a pull on just that 1 electron. So that's why you'll see more of an ionization energy. There's also another thing at work here, the difference between energy levels, which is another reason I like to look at Bohr models, because it's easy to see. When you're removing an electron from an outer energy level, that's going to take a lot less energy because it has that greater distance. So we're looking at both parts of Coulomb's law. We looked at the size of the charge already. Now we're looking at distance. The distance between the nucleus, where those positive charges are, and the valence shell is much greater than the nucleus and the core electrons. So the first ionization energy for lithium is much, much smaller than the second ionization energy. It's going to be less than the third ionization energy, but not as much, not as big of a difference. You're going to see the largest gap in ionization energies when you're changing energy levels. So let me look at some actual data. Let's say, for example, for sodium. Let's look at sodium now. Sodium's first ionization energy is 738. Its second ionization energy, no, I'm sorry, this is magnesium, my bad. Magnesium. Its second ionization energy is 1451, and its third ionization energy is 7,733. So do you see this one increases by like 700? This one increases by like 6,000. So you'll see that huge gap there because magnesium has 2 outer electrons, and the third one must be taken from a core energy level. For reference, its fourth ionization energy is 10,543. It's still more than the 7,000, but the jump is not as great. So this one increased by like 6,000, and this one only increased by like 3,000. So that tells you that like they're on the same energy level, but it's still larger based on the charge. So atomic radius refers to the size of an atom. If you picture an atom as like a circle or a sphere, you would measure it from the nucleus to that outermost shell. It's very difficult to measure, but I just want you to imagine it like that. You don't have to measure it yourself. But you do need to think about it in terms of Coulomb's law. So again, we're going to be looking at elements in the same group versus elements in the same period. So elements in the same group would be something like lithium and sodium. I'm going to be using these for a lot of my examples. There's lithium and there is sodium. They're in the same group on the periodic table. So they have the same number of outermost electrons and a very similar effective nuclear charge based on the shielding from sodium, from those core electrons in sodium. What's different then, of course, is the distance from that outer shell to the nucleus. And because there are more energy levels, sodium has a larger radius. Lithium will have the smaller radius because it has fewer energy levels. So whenever you're dealing with elements in the same group, you look at the number of energy levels. Now for beryllium, which is in the same period as lithium, but it has 2 valence electrons. Because they have the same number of valence electrons, the distance is actually pretty close, but not exactly the same. So they're not going to have exactly the same radius. What's going to affect it now is the charge. So lithium, remember, has 3 protons, 3 electrons. Beryllium has 4 protons and 4 electrons. Because beryllium has that greater charge, it has a greater attraction. Remember Coulomb's law. Because it has a greater attraction, it actually makes beryllium smaller than lithium. So beryllium has the smaller radius, whereas lithium has the larger radius when you're comparing those elements. So when you're looking at elements in the same period, you really want to look at the number of protons to see how that affects the pull on that outermost shell. Okay, so now let's talk about ionic radius. This doesn't come up a whole lot, but it does have an effect on the radius itself. So if I have a neutral atom of lithium, lithium has 3 protons and 3 electrons. Oops, I wrote EE, 3 electrons. Now, if I were to make an ion of lithium by adding an electron, it would now have, still has 3 protons, but now it has 4 electrons, and it would have a negative charge. If I take away an electron from lithium, it loses that whole outer shell because you have to take away the outermost electron first. So that lithium now still has 3 protons, but only 2 electrons. So positively charged ions will be smaller than their neutral atom because it's losing an electron, and sometimes it loses a whole shell. Negatively charged ions will be larger because you're adding an electron, the protons have less of an effect per electron. There's also what we call an increased electron-electron repulsion. Increased electron repulsion, because you have more electrons in the same shell, and electrons are all negatively charged, those same charges repel each other. And you can compare ionic radius for anything. You just need to get in the habit of looking at the number of protons, the number of electrons, and how they're organized. So whether they have all the same proton like this, or if they have different protons, different electrons, you can still compare them as long as you're looking at both the charge, that's the number of protons, and the size, the number of energy levels, so the distance. So electron affinity is kind of the opposite of ionization energy. Electron affinity is how much energy released when an atom gains an electron. So these are typically given as negative numbers because they're releasing energy. But we say the affinity for it, the attraction toward it, is greater when it has a larger negative number. So greater attraction to gain those electrons when you have a more negative number, because it's releasing more energy. And if you look on the periodic table, again, we're going to look at elements in the same group versus elements in the same period. Lithium versus, we'll do lithium and sodium again because it makes it easier. So if we want to gain an electron, it has to be attracted by the protons, the 3 protons in lithium or the 11 protons in sodium, and it has to come in from the outside. So this extra electron has to come in from somewhere else. So the protons have to be doing the attracting. So lithium, because its outermost shell is so close to the nucleus, it's going to have a greater attraction for electrons because that distance is reduced. Sodium, on the other hand, see how far away it is? And there's electrons blocking the protons from exerting as much charge. So sodium will have a weaker attraction for electrons based on that distance. The other trend, of course, would be looking at elements in the same period. So if you're looking at beryllium, beryllium has 4 protons, but a very similar distance to lithium. Right? So you have an extra electron coming in from the outside. Because it has those 4 protons instead of 3 protons, beryllium will have a greater attraction than lithium. Okay, the last trend we're going to look at is electronegativity. Electronegativity is the same concept as electron affinity, and it's how much the atom wants to attract electrons or gain electrons. But electronegativity is specific for elements are in a compound. For elements in a compound. So electron affinity is for atoms by themselves. Electronegativity is when they're in a compound or a molecule. But it follows the same exact pattern. As you have more protons, you'll have a greater electronegativity. So these numbers are not negative. So the greater the attraction, just the greater the electronegativity. And they're not negative values. So yes, you have more protons. They're going to have a greater electronegativity because it's a stronger attraction. But if you have more energy levels, you'll have a weaker attraction because it has a greater distance from the nucleus where the attraction and positive charge is coming from.